Hello, everyone. Thank you for the patience. We already have heard very many great talks in the previous session, and now we're here to listen to the talk of our keynote speaker for tonight. Let me present you Art B. Chmielewski, or how he likes to sign his emails ABC, who works at NASA JPL, where he plans future space missions. He has participated in 15 space missions and held almost every possible space job at NASA. He built space instruments for Mars rovers, installed nuclear generations on deep space spacecraft, designed billion-dollar space missions to the most unique destinations of our solar system, developed new technologies, and organized a lab to build a space telescope the size of a football stadium. He managed the missions that traveled to the Sun, Mars, Jupiter, and Saturn, and landed on a comet. He worked on getting images of cryovolcanoes, black holes, and extrasolar planets. Like that was not enough or not impressive enough. Art also was a consultant for Hollywood movies, designed space sculptures, and gave lectures at some of the most prestigious colleges around the world. He is a recipient of 5 NASA medals, 7 JPL awards, and numerous Polish awards. A note for the Polish audience, in Poland, he's also known as the son of Babcio Chmiel, famous for the cartoon series Tytus, Romek I Atomek, and an author of a just published book, Dare Mighty Things, Odważ się robić wielkie rzeczy, which was a #1 bestseller in Poland. Art is calling from the airport, so in order for him to not miss his connecting flight, his talk will be slightly shorter, and there will be no time for Q&A. However, don't worry, we will record all the questions and we will respond to them at the later time. So without further ado, ladies and gentlemen, Art B. Chmielewski.
Thank you. I'm glad that you already had some great talks. So this way we'll have some diversity of talks. There will be these great talks and there will be my talk, as I am the least professional person as far as astrobiology goes. Well, maybe then I should, my intro should be that I will represent my own personal views here, not NASA views. And this will get me off the hook. And I can present something that could be interesting. So let me share my screen here. Okay, here we go. You should be able to see my. Do you see my screen? Do you see my screen? Can you give me some feedback so I can proceed? Do you see the first slide?
Yes, we can see your screen.
Okay, awesome. Okay, so what I'm going to try to do in quick 20 minutes is to tell you, you are astrobiology, you're looking for life. So I'll tell you where are we going to fly to take your instruments and take your ideas and your brains to find life outside of our planet. Okay, so we at JPL, we build a lot of robots that, among other things, they look for life and carry all kinds of instruments. Or if they don't look for life per se, at least they are trying to establish if there's a habitat where life could evolve. So JPL is, I don't know, you probably already had this introduction. But this is the red dot on the map of the United States. And we're in a very pretty location, about equidistance from skiing and surfing. You can do this on one day. And we have about 6,000 engineers and scientists and about 30 deer, because our executive council thinks that petting zoo always relaxes people. Also, you can see the creativity. If you walk through the JPL parking lot, you can see the creativity on the brains. Everybody has a different personal license plate. Who am I? Ada introduced me, so I'm not going to go through this, but I've been on 15 space missions, serving different jobs, from designing one single component to being a project manager. And right now I I work in a formulation, which is planning future missions. And as Ada said, I am the son of Dr Chmiel, and you can see it in book number 3. Here I am in this blue suit showing the characters from my dad's cartoon, showing him rockets. And I told my dad, here you can see, my dad asked me over the phone, so son, what are you working on? And I told him, well, I work on instruments for spacecraft. So you can see that there are instruments on the spacecraft. Okay, so first of all, congratulations, you picked the right job, because astrobiology can really redefine the world. It's a still new field and always will be a new field. It's a very creative field, and you have many options. You can specialize, you can merge with other disciplines, geology, astronomy, engineering, and invent new ways of doing your research. But definitely what you're doing is daring mighty things, and this is our motto of JPL that we borrowed from Teddy Roosevelt in his speech. I think it was maybe 1910 or 1911. He made this phenomenal speech, but where he said, dare mighty things. And all of you are daring mighty things. So be proud of yourself and be glad that you're in this field. So, of course, when we plan new missions, sometimes we'll say, oh, okay, well, this mission doesn't seem ordinary, or is it really daring mighty things? Nobody has ever done this before, and this will be a breakthrough science. And if the answer is yes, then we go for it. And you could see this dare mighty things on the parachute of the Perseverance rover. So how that works, you can figure it out. But it's a description in binary. It's a binary message coded in the parachute. Okay. So Ada mentioned that I recently published a book in Poland. So, we all, in scientists and engineers, when we publish something, cover is not a consideration, but can't even imagine what you go through when you write a popular book that will be in the bookstores. First they gave me this cover, and then they said, well, you look angry. Some other people said, yeah, you look like an angry professor. That's good. And then they said, okay, the space should look black, not white. So they gave me black space. But then they said, it's too black. It's scary. I said, space is black and scary. And then they said, okay, blue is better. But why are you smiling? Why are you so happy? People will not take you seriously. So this is finally what ended up as a cover of this book. And of course, this says in Polish, dare mighty things. Okay, so we talk about 30 years, 30-year horizon for your discoveries. Why 30 years? Well, we're all enjoying these amazing pictures from James Webb Telescope, but I actually worked, not knowing that it would be called James Webb Telescope. I worked on it in 1998, 25 years ago, and we started this work almost 30 years ago. So that's how long it takes to develop technology. You can see here, of course, James Webb had these wonderful flexible thermal covers, because at that time we realized that any solid thermal cover will be just too heavy to be taken into space. So we started working on these flexible thermal covers. And this is a picture. This is the first prototype. It only had 2 layers, not 5 or 7 that on James Webb, but that was done 25 years ago, if you imagine, the first successful test. Okay, so I'm going to take you really quickly through the solar system, and you decide, or maybe you have already decided, which planet you're going to concentrate on. Okay, so first of all, before we fly, let's decide what life is, right? You all have these wonderful definitions. I read all these definitions, and I tell you, make it easier in engineers, okay? Because, we humans, engineers are good in recognizing life. Okay, this is life. Okay, this would be life. Okay, this probably would be life. This, I don't know. And We don't know. There's been a lot of discussion. But then, is this life? By definition, a lot of definitions, it has metabolism. It actually spreads, so it grows, so it moves, so it maybe procreates. By a lot of definitions, it would be life. This moves. It has a boundary. It also has metabolism. Is it life? Of course not. But I know you have this wonderful definition about the evolution. That it's a live organism capable of evolution. Well, I still don't know how to build a machine that would look at something for 5 million years and look if it evolves, right? Okay, but let's go through the solar system. We're going to skip maybe Mercury because there's not a whole lot of chance that there's life there, and we're not going to be looking for it, although there are some caveats, but we're going to skip it. So now we move to Venus. Of course, the holy grail of Venus exploration is the landing, but with 460 degrees, 100 atmospheres, and sulfuric acid, it's not an easy thing to do. But there are some concepts in how you could do it. Like here, this little thing in the right-hand corner is a steel balloon with a rotor that would power the refrigerator in this lander. But we don't expect any life, of course, to survive on the surface. We would be more interested in exploring even clouds. There have been a lot of hypotheses about life in phosphine and life in the clouds of Venus. So we're planning a mission, Aerobot mission. This is a variable altitude balloon with a gondola on which we have many scientific instruments that would determine the habitability of clouds at any place, right? Any altitude. Earth. Well, I am working on another mission sponsored by the Qatar Foundation, and the only reason I'm putting this here in this presentation is because we apply space technology that we used for Mars to Earth, and we're going to be doing things like trying to estimate the thickness of the ice in the Antarctic, right? And then we'll be looking for shallow aquifers in the Sahara Desert. And it's very important, not for finding life, but sustaining life on Earth. And by the way, sometimes I participate in these different discussions, and in one of them, Louis Friedman made a point that maybe, I think he was talking about his most recent book, is that we on Earth, that we most likely will find some life somewhere, but will we find intelligent life? We don't know, because we're not doing such a good job about sustaining our own life, right? Look at what's going on in the world right now: wars, conflicts, killings, climate change. So we have to treat each other and this planet a little bit better to sustain life. But of course, there is also Moon. We are not looking for life on Moon, but we're doing some really interesting thing. Is a proposal now to build an endurance rover. That would be a rover that would travel almost 2,000 kilometers and collect samples along the way and deliver them to the astronauts that will come on Artemis mission. So that's really exciting, and that's a new capability for rovers. I mean, Curiosity has been on Mars, only traveled in 12 years, I think something like 30 kilometers. Moving to Mars, of course, there's Perseverance, Curiosity, Ingenuity. We're going to have Mars sample return. That'll be extra exciting. We're trying to change the architecture of the mission to make it a little bit more a little less risky. But this is a flagship mission by all means, and will consume the agency, but at the same time, we'll be doing a lot of other research. This is a concept of how we use little sample return helicopters to do some science, and these scientific packages that the helicopters would drop on Mars would be called tube bots. That would be tiny little instruments, 150 grams. If you have some ideas what you could do with 150 grams, then you definitely want to talk to you. And then after that is Condor. That's a large helicopter, 5 kilograms of instrumentation, and it may fly for hundreds of kilometers and get to places where rovers can't. We're working on it right now. I saw the first almost an engineering model at Caltech a couple of days ago. Also, okay, we're looking for life, but we have to protect this life here. And we're planning on rendezvous mission to Apophis. Apophis will be this 340-meter asteroid that will be coming for a close shave of Earth. Will not hit us, but that will be darn close. As a matter of fact, you'll be able to see it with naked eyes. On April 13th, Friday the 13th, what could go wrong? Very exciting mission. We can talk about it some other time. Jupiter, of course. Jupiter is exciting because it led to all the discovery that there's just so much water. It just can't see it. It's under the ice. But look how much water these blue bubbles represent. The amount of water are on each of these planets or moons, and how little there is on Earth in comparison, for example, to Titan, right? And this is what it looks like. So, life may exist. There are thermal vents, right? You've seen this picture many, many times, so I'm not going to talk about it. But that's where the glory is, to get into the ocean. Depending what the European mission JUICE and Europa Clipper will show, maybe we'll go for a lander if there's a promise of something exciting. Lander on Europa, tough call. And what instruments will it carry? Saturn. Of course, that's my favorite picture, and because we're looking at the Cassini spacecraft is looking at us here. We're size of 4 or 5 pixels, but that, to me, I always, whenever I'm unhappy about something, somebody is irritating me, then I look at this and I say, I'm now only living on these 5 pixels. So in the empty space. So how could I, be? This is such a little thing. It's just not worth even thinking about. But of course, the moon of Saturn Enceladus, that's a very exciting, carries a lot of promise for possible life underneath the ice sheets. And one of the ideas of exploring Enceladus would be with eels, these robotic machines that kind of look like eels, like snakes, and they will go get into the cracks in the ice and try to get all the way down to the ocean. Very difficult technology, but we're working on it. 30 years, maybe faster. Titan goes surface ocean under the ground. There's so surface ocean is methane and ethane, and at 94 Kelvin, we shouldn't be expecting life there, but the water ocean underneath, who knows? We're sending Dragonfly, built by Applied Physics Lab. We wish them great luck. A phenomenal mission. And of course, when Dragonfly won, I was a so-called capture lead of a proposal that was competing with Dragonfly, and it had a submarine kind of a boat to explore the lakes, but I lost. And then of course Uranus and Neptune. Uranus, very exciting. We're planning the next flagship mission to Uranus. What is it, 23, 27 moons, something like that, lying on its size, changing magnetic field, amazing. And on the top of that, most of the planets, extrasolar planets that we're discovering, they look like Neptune or Uranus, not like rocky planets. So, and we know very little about them. So this will be very exciting. And there will be an orbiter and there will be a probe. The probe will drop into the atmosphere of Uranus and will give us first time the data on composition and pressure and temperature of the atmosphere at Uranus. And Neptune, a very exciting place from the point of view because it has an ocean world. It has a Triton, which is possibly a captured object, but it's expected to have ocean underneath this ice layers. So that would be terrific to explore it. And I worked on proposing a mission called Trident. And this was a flyby, but it would give us a very good idea if Triton has an ocean underneath. A very exciting mission. It was not selected, but Venus missions were selected. But nevertheless, it's, we'll try again. So this ends my talk, and I'm going to leave you with some action items because some of you are students. You're used to getting action items, right? Homework. Okay. So first of all, I need a better definition of life from you and how I can discover it. So we can build better instruments for you. And then we'll give it to you. You'll find life. So let's just do it. You'll have 30 years to do it. Thank you.
Art, thank you so much for your insights for the next 30 years of space exploration and the good advice you left with the students. We hope you'll make your connecting flight, and we'll see you next time.
I'm running now. Thank you so much for inviting me. Super exciting conference, and I'll be glad to answer questions when I land in Warsaw. Thank you.
We'll make sure to send those to you. And for all the other participants of the conference, we will now have a second networking session.
Thank you.